So this is really general, completely general to any type of experiment where we have a sample space of equally likely outcomes. So if we have an event E and event F, we could define the probability of E given F to be the size of E intersect F over the size of F. That is, we only consider outcomes that are in both E, the event E, and the given event F, divided by the total number of outcomes that are in F, because we're only considering the ones in F since that's our given information, right? We're presupposing that the outcome is in F to begin with, and we want to know the probability that it's also in E, which is why we do the size of E in F, size of E intersect F, I should say, divided by the size of F, right? So that's completely general. Now what we can do also is we can change this fraction a little to get an equivalent definition here. So if we were to divide both the numerator and denominator by the size of S, or the size of the sample space, and again we're dealing with equally likely outcomes, then what we have in the numerator is actually the probability of E intersect F, right? It's the size of E intersect F divided by the size of the sample space, and since each of these outcomes are equally likely, this will be the probability. And in the denominator, we'd have similarly just the probability of F, right? Because we're doing the ratio of the size of F to the size of S. And this P E given F is equal to the probability of E intersect F divided by the probability of F is the definition we use in general for conditional probability. So let's look at that in this specific case with equally likely outcomes. This example here. So we had the 20,000 scheduled class days. So we're going to say that the probability of the sample space, right, that should just be 1. It's 20,000 over 20,000. And I'm also now going to change the events, the variables representing the events. So I don't use F for both, for F for all Hindi, day in February and day in May. So I'll use H for Hindi and F for February and M for May. So we say that the probability that the day is in S, right, is just going to be 20,000 over 20,000 or 1, right? This is also the probability that it is in H, because H is going to be the same as S, right? It's all the days when Hindi was spoken somewhere. Now, if we look at the 100 days of canceled classes due to snow, this is going to be the probability of E, as before. We'll also say it's the probability of E intersect H, because H, again, is just going to be S, and as we said, E intersect the sample space is just going to be E, since E is a subset of the sample space. We could also consider the probability of F, right, which is just going to be the 1,400 over 20,000, right, because there were 14 scheduled class days in February, and 20,000 total days. We could say the probability of the event M, or being a scheduled class day in May, is 1,300 over 20,000. Since we said there are 35 days of canceled class due to snow in February, we would say that this is the probability that we're talking about a day that was canceled due to snow and is also in February. So that's the probability of E intersect F, which is going to be the total number of days canceled in February due to snow, which is 35, divided by the total number of days. Scheduled class days overall is 20,000. And similarly, we would have the probability of E intersect M, which is going to be the canceled days in May. The probability of having a canceled day in May is just going to be the 0 over 20,000. So from the definition before, which again is our general definition of conditional probability, we see we get the same results. The probability of the snow day is P of E. It's going to be 100 over 20,000, or the 0.5%, right? That's just from here. The probability of E given M, right, we said is going to be the probability of E intersect M. That's the probability that we are talking about a snow day that's also in May, which was 0, divided by the probability that we were just taking a day in May, which was 1,300 over 20,000, or 0.065, right? You do the 0 over 0.065, you get 0. So we could also consider, again, the probability that it snows, or that we had a snow day, given that it was a scheduled day in February, and that's just going to be the probability of E intersect F, right, which was up here. That's the 0.00175, or the probability that we had a canceled day and it was in February, divided by the probability of being a day in February, a class day during February, which was 1,400 over 20,000, or 0.07. And if we divide those two numbers, we get the same 2.5%. And of course, you could also just see this from doing 35 divided by 20,000 over 1,400 divided by 20,000. The 20,000s are going to cancel, and we're just going to get the 35 over 1,400, which was, again, the number of days in both February and snowed over the total number of days in February. And finally, we could just talk about the probability that we had a snow day given Hindi was spoken somewhere that day. So P of E given H, that's going to be the probability of E intersect H over the probability of H. We said that the probability of E intersect H is equal to the probability of E, right? Because E intersect H is just going to be E. And the probability of H, again, because H is S, that probability is just 1. So we have the probability of E over 1, which is just the probability of E, which is the same 0.5%. And one thing I want to point out here is you notice that the probability of E given H is equal to the probability of E, and that's actually going to mean that the two events, E and H, are independent of each other, right? The probability of E doesn't change even with the given information H. It still stays the probability of E. So in general, the conditional probability for a sample space S, an event E, and an event F, with the probability of F being greater than 0, the conditional probability of E given F, which we again denote P with E vertical bar F, is going to be defined to be the probability of E intersect F. That means the probability that the outcome is both an E and F, divided by the probability of F itself. So we could say that the event E is independent of F, right? So it doesn't depend on F when the probability of E given F is just equal to the probability of E. So as we said as the example, when the event F was really corresponding to the event H of Hindi being spoken, we said that the event E of there being a snow day was independent of Hindi being spoken on that day, right? So the probability of E given H was 0.005, which was the same as the probability of E itself, or just the probability that we had a snow day. And in general, any event E is going to be independent of the event corresponding to the entire sample space S, right? So again, here we had H was equal to S, so the probability of E given H was equal to the probability of E given S. And anytime you have the probability of E given S, it's just going to be by this definition over here, right, where F is S. It's just going to be the probability of E intersect S over the probability of S. And again, since the event E is going to be a subset of the sample space S, E intersect S is just going to be E, so we're going to have the probability of E in the numerator, and the probability of the entire sample space S is just 1. So we're just going to get the probability of E over 1, which is just going to equal probability of E. So anytime you're talking about the sample space S, any event is going to be independent of the entire sample space, which makes sense because we know that some outcome in S will occur just by definition. So given the information that an outcome in S occurred, that doesn't tell us anything new about whether one of the outcomes in E is going to occur or not. So it remains the probability of E given that extra information that the outcome is in S is still going to be the probability of E. Okay, so to summarize what we talked about in this lecture, the conditional probability of an event E given an event with a non-zero probability F is defined to be the probability of E intersect F, so the probability that the outcome is in both E and F, divided by the probability of F, so the probability that the outcome is in F. Right? In the case where we're talking about an experiment with equally likely outcomes, such as the roll of a die, we could just count the number of outcomes that are in both E and F and divide that by the total number of outcomes in F. Right? And the probability of an event E, such as having a day of classes canceled due to snow, can either increase, right? So the probability of E given F could be greater than the probability of E, when F was being a day in February. So the conditional probability of E could increase with additional information F, or it could decrease with the given information or event F, such as the case when F was being a day in May, right? So in this case, we had the probability of E, or the probability that it snowed, given that we were in May, is going to be less than the probability of having a snow day overall. Or it could stay the same, right? And if it stays the same, such as the event F being that Hindi was spoken on that day, that doesn't give us any new information, then we would say that the events are independent, right? So the event of us having a snow day, a snow day on a scheduled day of classes, is independent of whether Hindi is spoken that day or not, right? So probability of E given F is equal to the probability of E, so it doesn't change. And finally, I want to make one note here that the probability of E given F is different from the probability of E intersect F, right? So the probability of E intersect F says that we're trying to find the probability that the outcome is common to both E and F, right? We're trying to find that the probability that both E and F happen together. Whereas the probability of E given F is saying, okay, we already know that an outcome in F occurred, so what's the probability of E? What's the probability of getting an outcome in E? Right? So in general, we'll always have the probability of E given F is greater than or equal to the probability of E intersect F. You could see this right from the definition here, because the probability of F is going to be between 0 and 1. Actually, it's not going to be 0, right? That was our assumption when we're doing the probability of E given F. We say that the event F is the probability of that has to be non-zero. So we know this is a number that's greater than 0, and it's going to be less than or equal to 1. And if we divide by a number that's between 0 and 1, right? If it's 1 exactly, that's just going to be getting the same number that you have in the numerator. But if it's less than 1, if it's a positive number less than 1, then that's going to actually the fraction is going to be greater than the quantity in the numerator, right? So if the probability of F was, let's say, 1/2, we would be multiplying this probability in the numerator by 2. So the probability of E given F is always going to be greater than or equal to the probability of E intersect F. And again, that makes sense because the probability of E intersect F is saying that the two events have to occur together, whereas the probability of E given F is saying we already know that F occurred and we just want to know that E is going to occur. So that's basically the end of today's lecture, and we'll continue in the next lecture with some more advanced conditional probability.